Okay, greetings aspiring scientists. Welcome to my video today on oxidation states. This is going to be one of the most important videos that I do, I think, right up there with Lewis structures and electron configurations, because not only might you be asked specific questions about oxidation states, but it's a tool that you can use to solve many other questions that just give you complicated reactions or ask you to predict what's going to happen in certain situations. Very powerful tool. Anyway, let's go to my slides. So we are in 3.1.6 now in the classification of matter, still in kind of the periodic table section, but this is all about oxidation states today. So we're just going to define it, go over some rules, and then do a bunch of practice. So oxidation states, also known as oxidation number. So we have seen oxidation states used to describe the charges on ionic compounds. It's often the number in the top right that tells you how many electrons have been lost or gained. Now, this notation that we've used for ionic compounds and ions can also be used for covalent compounds that do not contain full ions. And this way of numbering elements assumes that they are ions, or that they gain or lose electrons. Even though they don't, at least not 100%, we can assume that they do and assign numbers to them. So this means that when there is no electronegativity difference, even in a covalent bond where electrons are shared, the oxidation state and the change in oxidation state would be zero. But when there are differences in electronegativity, then one atom will pull the electrons closer to it, and then the more electronegative element gets the electron, and therefore we'll get a more negative oxidation state number. So let's look at an example. Here is water. So water has no electric charge. It has no what we call formal charge either. That means within the molecule there is no positive or negative full charges. But there are partial charges due to the fact that oxygen is more electronegative than hydrogen. So oxygen does not have a formal charge of -2, but it does have an oxidation number of -2 in the compound water. This oxidation state is a system that just indicates which element holds the electrons closer. So you could imagine in a perfectly balanced bond, the electron pair would be kind of shared exactly equally at this bonding location. 50% density to each atom. But we know that oxygen is more electronegative, so it's going to pull these past the 50% line. It's going to hold more density than 50%. So we say that it gets the electrons. And since it had 6 to start in its valence, and it sort of borrowed 2 from these hydrogens, that's where the -2 comes from. Now, hydrogen then loses its electron in this sharing pair. Not 100%, but it's enough. It's past that 50% line, so we can say that its oxidation state is +1 on each of these. Okay, hopefully that makes some sense. So there's a set of rules. I'm going to say you must remember these rules. A lot of them are fairly easy and obvious. Some of them not so much though, and it definitely takes a bit of practice. So rule number 1, free elements or pure elements have an oxidation state of 0. So this could be something like, I don't know, sodium metal, oxygen gas, bromine liquid. As long as there's only one type of atom, the oxidation state is 0 on that atom. Even something like S8, with like 8 sulfurs in a ring, they still can't pull the electrons past that 50% line, so they share them equally, so oxidation state is 0. Next, rule number 2. For neutral compounds, the sum of all states is 0. That means if your compound has no net electric charge in the top right corner, That means the sum, if you add up each individual atom's oxidation state in that, it must come out to 0, because the sum is what the total charge on the compound becomes. Okay, number 3, for charged compounds, the sum of all oxidation states is equal to the charge on the compound. So we're talking about charged ions here, maybe polyatomic ions like sulfate, nitrate, phosphate, whatever, ammonium. Those have charges in the top right. They're charged compounds. So that means the sum, adding all of the oxidation states of individual atoms inside them together, must equal that total charge on the ion. Okay, so these first 3 rules, they cannot be broken, okay? This is just how things are. These 3 rules cannot be broken. You'll see I have an arrow here on the top, or on the right side of my slide, that says strictness. So strictness increases as you go up these rules from number 7 to number 1. So especially these first 3 rules cannot be broken. Rule number 4 also pretty much cannot be broken. I've never heard of such a rule being broken, but the oxidation state of fluorine is -1 when it's not a pure element. If it's in any compound, it takes an electron because it's the most electronegative element with 4.0 on the Pauling scale. If it has any interaction with another atom, it takes the electron. So it gets the oxidation state -1. Rule number 5, the oxidation state of alkali metals is +1, and the oxidation state of alkaline earth metals is +2. So these are metals with very low ionization energy. When they form chemical bonds with anything other than themselves, they will lose their electrons because basically anything else is more electronegative, so it will take the electrons from these guys. Now we're kind of in the middle of the strictness scale here. This is pretty much always true, but you might come across some cases where like alkali metals form an amalgam or a bond or a solution with each other where there is electronegativity differences among those metals and one gains the electron more than it loses. That is possible, although you'll almost never come across those examples in high school in IB. Okay, rule number 6, the oxidation state of oxygen is usually -2. I'd say 95% of the time, -2. But there are notable exceptions, some here, like OF2. And H2O2. So hopefully if you've been following rule number 4, you'll understand why OF2, oxygen, cannot have an oxidation state of -2. Fluorine takes the electrons. Fluorine is more electronegative, so oxygen will go plus in that case, plus oxidation state. Now H2O2. It would be helpful if you recognize what the Lewis structure of this is. Basically, this will have an oxygen-oxygen bond and then 2 oxygen-hydrogen bonds. This is the way oxygen completes its octet in peroxide. Like this. So you can see oxygen will take an electron from the hydrogens. Oxygen is more electronegative, but it cannot take an electron from the oxygen-oxygen bond in the middle. That is very similar to a pure element bond, O with O. So the electron pair there is exactly 50% held. You can't say which oxygen would go plus and which would go minus. So they end up being 0 there. In that case, the oxygen oxidation state in peroxide is just -1. The hydrogens are, though, +1. So you can see that this follows rule number 2. We'll have 2 hydrogens at +1 and 2 oxygens at -1, and the charge on the neutral compound is 0, so they cancel out. Okay, rule number 7 then, where things get very flexible, is hydrogen. Hydrogen can be +1 or -1 depending on if its bond is with a metal. If it's with a metal, hydrogen will get the electrons and go -1. If it's with a non-metal, hydrogen will lose the electrons usually and go +1. But you got to be aware of what you're looking at and consider all possibilities. And oftentimes hydrogen might be something that you want to solve for in the end as an unknown. We'll go through that soon. So definitely remember these 7 rules. Remember that strictness increases as it goes up. So you kind of also have to remember the order and the strictness of these rules. But another way to think about it is the halogens almost always go -1, especially fluorine. But as you would go down the periodic table, you get into expanded octets. That's an HL topic, but it is possible for halogens to lose all their electrons instead of gain. So be aware there are some exceptions again. And then the alkali metals and alkaline earth metals on the other side of the periodic table, much more likely to lose their electrons. Okay, moving on. Now there is an equation or a method that you can use to find almost any atom's oxidation state in any compound, but it will take into account the rules on the previous slide. But if you have a situation where you have any compound, AX, BY, CZ, and so on and so on and so on, all with a charge of N in the top right, the oxidation state of A and B and whatever else can be found with X multiplied by the oxidation state of A plus Y multiplied by the oxidation state of B plus Z multiplied by the oxidation state of C, and so on until you've covered all the atoms. That will equal the total charge on the complex, the compound. That's rule 2 and 3. So let's look at an example. Sulfate SO4 2-. You can split the S and the O. So S has a subscript of 1. There's just 1. So 1 times the oxidation state of S. We're going to solve for that because it's not as clear. It's not part of the rules. And then for O, we'll have 4 O's, 4 multiplied by -2, because oxygen is almost always -2. In this case, all the oxygen bonds will be with sulfur. That's something you should realize if you're good at drawing loose structures. But 4 times -2, this will equal the total charge -2 in the top right-hand corner. Then this can just be solved. You can just label oxidation state of S as some unknown value, X or whatever. Solve it. So X -8 equals -2. That X is +6. The oxidation state of S is +6 in sulfate. So all the oxygens surrounding that sulfur pull the electron pairs closer to them. Sulfur essentially loses all of its 6 valence electrons. Not fully, but over that 50% line. Then a final rule, very important. Oxidation states are written as a mathematical sign, plus or minus, then a number, 1, 2, 3, 4, whatever. Not as number and then sign. And I know this is confusing because when we write just a chemical formula or an ion nuclear notation, we do write number and sign, right? 2-, 3+, or even just a minus and a plus sometimes without the number. That's not how we write oxidation states officially. So examples of them written properly would be an oxidation state -2, +4, -1, that's good. You can't write 2-, 4+, or just minus or plus. They have to have a number. And IB is very strict about this. They will not give you the point if you write the sign in the wrong place. Okay, so write the sign first, then the number when you're solving an oxidation state question. Okay, let's do some practice here. Practice the following. What's the oxidation state of H2, Cu, Zn, Xe, and Au? So that's hydrogen gas, copper metal, zinc metal, xenon, noble gas, and gold metal. So it seems like a lot of work, but rule number 1, I think, right? Pure elements, oxidation state is 0. These will not be taking or losing electrons to anything. Oxidation state is 0 pure elements. Okay, then B, the P atom in phosphate. So phosphate is a polyatomic ion I've recommended everybody memorize. If you remember, this is going to be PO4 3- charge. So use the calculation method. We know oxygen is almost always -2. We have no reason to assume that it's not in this. It's more electronegative than phosphorus, and there's unlikely to be any OO bonds. So we can set up P, there's one of those, plus 4 times the oxidation state of oxygen is -2, usually. This will equal the total charge on this complex, -3. So we will have P minus 8 equals -3. That means P is equal to +5 oxidation state. So that phosphorus will lose all of its electrons to oxygens in this compound. Mn then in KMnO4. We can do the same thing here. So K is an alkali metal. There's a rule for that. O is oxygen. There's a rule for that. So it's really the Mn that I don't know. I'm going to use this as my unknown, Mn. Plus 1 for alkali metal potassium. Plus 4 oxygens again. These will be -2. This equals 0 on the total compound. So I'm going to have M plus 1 minus 8. Or in other words, M minus 7 equals 0. Sorry, Mn minus 7 equals 0. Mn equals plus 7. So the oxidation state of manganese in this is +7. Transition metals, excuse me, like manganese or metals in the middle of the periodic table can often have very high oxidation states. I think 7 is pretty much the highest, but beware. This is not that crazy. It's a common oxidation state from manganese. D then, all atoms in LiAlF4. So Li, another alkali metal, we can assume it's +1. F we know is -1, so it's really Al that we want to solve for maybe. Al plus 1 for lithium, plus 4 times -1 for fluorine, equals 0. There's no charge on this total. So we're going to have aluminum Al plus 1 minus 4 is -3 equals 0. So Al must be +3, and that is a very common oxidation state for aluminum, which is in group 13 under boron. Now this question does say label all of them, so I will also write, we knew Li as an alkali metal is +1. We know F, when it is in compounds, is always -1. Okay, good practice, but I do have much more. So here's a bunch. If you want to try it yourself, you can pause the video, try it, and then I'll go through each one. So, starting with CO2. Oxygen we know is going to be -2, so let's do this. C plus 2 times -2 equals 0. So we'll have C minus 4 equals 0. That means C is +4. And this does say label all the states, so I'll also write O equals -2 in CO2. Good. B then, CH4. This is pretty tough. There's not a lot of clear whole rules about this, but remember that when hydrogen is with non-metals, generally it's going to lose its electron. So we can have C as our unknown, plus 4 times H with a non-metal, so H is going to go plus 1. Neutral compound, 0 charge. So we will have C plus 4 equals 0, C equals minus 4. And we did assume H goes plus 1. Done. Okay, C. K2, Cr2O7. Looks pretty tough, but remember there are rules for K and rules for O. So it's just Cr that we're trying to find, but there are 2 of this. You got to take into account all of the subscripts. So 2 chromiums plus 2 alkali metals. It's 2 times plus 1 plus 7 oxygens. They are minus 2 each, usually. This will equal 0. So we'll have 2 chromiums plus 2 minus 14. It's minus 12. So 2Cr equals plus 12. Cr equals plus 6. Again, it's a transition metal. It can have commonly high oxidation states. And we did make some assumptions there about the other ones. O is minus 2. And K is plus 1 by following the rules. Okay, let's move over here for D. OF2. Warning, this is an exception compound. Fluorine has very high oxidation state, so we're going to choose O as our unknown, even though it's usually minus 2. We know it can't be here. Plus 2 times fluorine. They are minus 1 if they're in a compound. That equals 0. So O minus 2 equals 0, O equals plus 2. One of the only times oxygen will go positive oxidation state. But this is a compound that is sometimes made and used, I think, in like rocket fuel or something, although its instability makes it not very useful. Okay, EHClO4, pretty tough. In this case, Cl is not in the rules anywhere, although halogens usually go minus 1. Sometimes the lower ones will go plus instead, and this is a lower one, lower than fluorine. It can have an expanded octet. So we'll keep Cl as the unknown one to solve for. We'll have 4 oxygens. We can still assume that they will go minus 2. And we have 1 hydrogen. All the other things here are non-metals, so this hydrogen is going to go plus 1. This equals 0. So we will have Cl minus 8 plus 1, it's minus 7. Cl equals plus 7. It loses all of its valence electrons and goes to the most recent noble gas configuration. Somewhat uncommon, but definitely possible. And so we've said, we made an assumption that O is minus 2. H is plus 1. So those are our answers. Oh, I forgot to label in D that F is minus 1. Okay, F, NaH, sodium hydride. We know what sodium will do, and hydrogen, when with a metal, will go minus. We'll still use it as the unknown though, so H plus 1 for sodium equals 0. H equals minus 1. and sodium is +1, we assumed. Okay, let's go G, Fe2O3. Fe we'll choose as the unknown. Oxygen's going to go -2. 2Fe plus 3 times -2 equals 0. So we're going to have 2Fe equals +6. Just rearrange this a little bit. And then Fe equals +3. And we did assume O equals -2. Done. Okay, H, let's go in the middle here. SO3E2-, this is a polyatomic ion. So instead of setting it to 0, we're going to set it to -2. We'll use S as the unknown, plus 3 oxygens at -2 each. And this equals -2. Okay, so we'll have S -6 equals -2, or S equals +4. So this is a different oxidation state than in normal sulfate. This is a less oxidized version called sulfite. And we did assume O is -2 here. All right. HI next. Na2O2. Be very careful here, okay? Usually O is 2-, usually Na is +1, but we have to break a rule here because they can't both be true to make this equal 0. It must equal 0. So which rule can be broken less? And the answer is the sodium one. Alkali metals will lose their electron almost always, especially sodium up there. So we'll choose O as our unknown. And we have 2 of those, 2O plus 2Na, that will be +1. This equals 0. So 2O equals -2, O equals -1. So it turns out that this compound is very similar to hydrogen peroxide, another exception I wrote on a previous slide. Hydrogen peroxide I drew like this. An OO bond and some OH bonds. Well, sodium peroxide is essentially the same thing. It's just instead of hydrogens, there'll be sodiums instead, and it's not a covalent bond, it's an ionic bond. So the sodiums are just positive, and the oxygen kind of has got an electron somewhere and is negative. Very weird structure, but it's like if you took hydrogen peroxide and you stripped the H's off and replaced them with sodium cations, this could be made. Anyway, so O is -1 in this because it doesn't gain or lose any electrons from the OO bond. Only it has received an electron from somewhere in its negative charge region. Okay, I'm out of space, but I got 2 more, so I'm just going to clear this. Okay, J next. CH3OH, kind of tricky. I would recommend labeling C as your unknown because it is not in the rules directly, and it, similar to hydrogen, can go plus or minus fairly often. We do then have an oxygen that will go -2. And we have 4 hydrogens. They're all with non-metals, so they're going to go +1. This will be equal to 0. So we can simplify this a bit. -2 plus 4. C plus 2 equals 0. C equals -2. And we made some assumptions there. O is -2. H is +1. Okay, and if you draw the Lewis structure, this should make some sense. We have a COH, and then 3 CH bonds. So in the H bonds, C will get the electron pairs, pull them close to itself. But in the CO bond, it loses the electron. Oxygen, being more electronegative, pulls it. So it kind of goes -3, but then +1. So in the end, that's how it gets the -2 oxidation state. It goes -3 from hydrogens, but then +1 from the oxygen. All right, then the last one, KCH2O, another organic compound. Again, let's use C as the unknown. We're going to have an oxygen, -2 for that. We're going to have 2 hydrogens. They'll be +1. No net charge, so 0 there. So this time, C -2 plus 2 equals 0, so C equals 0. And we did assume O is -2. Hydrogen is +1. If you draw the structure of this, it should also make sense. This will be a carbon-oxygen double bond and then 2 CH single bonds. So C goes -1 for each of these hydrogens, pulls these electrons close, gets the electron. But with the CO bond, it loses all those pairs. Those 2 pairs get pulled to oxygen, so C goes -2 from that. C goes +2 from that as oxygen takes them. So it's -2 from H's, +2 from the oxygens. That's the net oxidation state of 0, which is the same as if carbon was in its natural pure form. Even though this is a very different compound, this just shows you that it can still have a 0 oxidation state, even in a compound like this, if it's losing electrons to some neighbors and gaining electrons from other neighbors. Okay. So a couple more things with oxyanions and naming. I've asked you to memorize some polyatomic ions with 8 and ite. That's the common naming system. But there is a more universal and potentially clearer system using Roman numerals, which clearly shows the oxidation state of central atoms. So you really need to know the Roman numerals in chemistry. I'll draw them at the top here quickly. 1, 2, 3, 4, 5. So you can kind of see that a 1 before a 5 means a 4. It's like 5 minus 1. A 1 after a 5 is a 6. 2 after a 5 is a 7. And I think that's basically as high as we need to know. So 1, 2, 3, 4, 5, 6, 7. Know how to use these. So for positive oxidation states, the number on the oxidation state is written after the oxoanion. We'll write the 8 name. and then the Roman numeral. So for example, SO42-, we can write sulfate bracket 6. That means it has an oxidation state of +6. But other ones are possible. You can have sulfate 4, like we saw in a previous slide, that's SO32-, a less oxidized version. So that's how this naming system could slightly be clearer, but you definitely need to know how to read it and use it. So here are some common ones: nitrite and nitrate. So nitrate is nitrate 5 oxidation state. Nitrite, though, is just labeled nitrate 3 in brackets. It's only a +3 oxidation state on N. Sulfite and sulfate, as I said, we can have sulfate 6 and sulfate 4. They have different numbers of oxygens and different amount of oxidation on the central non-metal atom. So final practice then, we can do some of these. Write the chemical formula for the following named compounds. Sodium phosphate. So I've just showed on one of the previous slides that phosphate is PO4 3-. The phosphorus in this is +5. We solved that on a previous slide, I'm sure. So that means this compound can just be labeled as NaPO4, and we would need 3 sodiums to balance that 3- charge on the phosphate. But the 5 does match the oxidation state in this. So that's good. Na3PO4. Hydrogen nitrate then. So this doesn't have any Roman numeral. That means it's not the new naming system I told you. It's the old casual naming system. So you just need to remember the nitrate formula is NO3-. And hydrogen nitrate means that this charge will be balanced just by an H+. So this will be HNO3, otherwise known as nitric acid, from the nitric rain video I made last week. Nitric acid rain video I made last week. HNO3. Okay, magnesium bromate. I think this one is very tough, and if you're not an expert, you're probably not going to get this right. So regular bromate. It's not even one I ask you to memorize, but I think you guys might like to know the halogen 8s. The base form of them is O3, XO3. So we can have ClO3, BrO3, IO3. This is the 8 casual name of all of these halogen oxoanions. Now, we can also have per versions of this. So perchlorate, perbromate, periodate, perfluorate. These will have extra oxygen or oxidation. So you're going to have XO4. Now I think all these do still have a -1 charge, even the per versions. But there is then less oxidized versions containing less oxygens. So these ones here are the 8 versions. These per ones are the per 8 versions. Perfluorate, perbromate, periodate. But there is ite versions. These would have 2 oxygens only, so XO2-. Bromite, chlorite, iodite, fluorite. So when we're looking at this, magnesium bromate 3, bromate in this Roman numeral version encapsulates possibly all of these, the per version, the ite version, the regular version, but it's the Roman numeral 3 that will tell you which it is. So you have to really think about this. You might start assuming that it's regular bromate. Regular bromate is BrO3-. But then you better find the oxidation state for that. Br plus 3 times minus 2 equals minus 1. Br minus 6 equals minus 1. So Br equals plus 5. Oh no. So this would only be the answer if this was magnesium bromate 5 with a Roman numeral V like this. So it can't be this. You got to try one of the other ones. This is a less oxidized version, so you're going to want to try that ite version, less oxidized one. And if you do try that though, Br plus only 2 oxygens, 2 times minus 2 equals, still has a charge of minus 1. But in this case, this will be Br minus 4 equals plus 1. Sorry, Br minus 4 equals minus 1. Therefore, Br equals plus 3. That is what we need. We need that triple Roman numeral on the bromine, the central atom in the oxoanion. So this must be magnesium. The bromite has a minus 1 charge, so it needs to be 2 of this to perfectly balance Mg2+, an alkaline earth metal, BrO2 twice. Very difficult formula to solve from this name, but it is possible. If you're curious about the Lewis structure of BrO2- or any of the halogens, I think it will look like, draw it here in this only empty space remaining. Br with 2 lone pairs not participating, an oxygen that has the negative charge of BrO2-, and then a double bond oxygen. Very difficult. Really, it's an HL kind of Lewis structure. So if you didn't get this, or if you don't think you could get this, it's not the end of the world. This is like the most advanced one I can think of. But it is in a textbook from the Oxford Course Companion, so if you're curious, this is how I would solve it. You have to know some things about the halogen oxoanions, though. Okay, I'm just going to clear this page as I do the last one. Potassium sulfite with no numeral, that means we're using the casual name. Sulfate SO4 2- is the regular version of sulfate oxoanion. Ite, ITE, means it's less oxidized, so SO3 2-, same charge though. So potassium, we're going to need 2 of those to balance with SO3 2-. Sorry, this is SO3. Just let me write that a little bit more clearly. Okay, then we're done. I think that's all I have for today, so we'll finish there. So that brings us to the end of the periodic table section of the textbook for SL. Next time we'll move on to organic chemistry, my absolute favorite topic. A lot of people say it's tough, but it's definitely what I've studied the most, probably 5 times more than any of these other topics. So I'm looking forward to making the video. Hope you learned something. See you next time. Bye-bye.